This is your canvas. I did put in the lecture last time. It's up online. Today we're doing gas laws. We are going to do Boyle's Law lab. I'm pushing Graham's Law to next time with the molar volume of gas. Both of those will be back in the very back lab, so we don't have to keep going clear to the very back lab and coming back and forth and back and forth. So that'll actually work better. We just ran out of time for fifth period to do it, so that's what I'm doing for L periods. So make sure that you remember that up through 6.4 in sapling and quizzes is due next Friday, so do not wait to get started on sapling. Okay, get going on it. Lab notebooks are also due next Friday, so the labs that we do going up to that and including that day will be in your lab notebook turned in on Friday so that I can get them recorded into your grades. Okay, anything after 6.4 will be due next term. Test is open 18th through the 24th. That is a Thursday through a Wednesday. So it's over a weekend, but it's a Thursday through a Wednesday. So make sure you find a time during that period to take that test. Any questions with what's going on here? Okay, going forward. And I forgot to... Okay, so last time we did kinetics. Those were the toddler rules, I remember. Kinetic theory was toddler rules. Who can remember the 5 toddler rules? No what? No volume. Random straight line motion, okay. Elastic collisions. No repelling or retracting. Is directly related to energy. Good. So there's our 5 toddler rules. So remember that was for ideal gases. Ideal gases, the kinetic theory. What happens when we get real? In other words, when we become teenagers, 3 things are different. What are they? I do attract and repel. Non-elastic collisions. And I have volume. Good. How do I get ideal gases, or real gases, to act more ideal? There's 3 ways. Low pressure, high temperature, non-polar situations. Good. So I get to choose the friends I hang with. So that was summertime, right? Teenagers are happy in the summertime. All right, so what we're going to do today is we're going to talk about the kinetic theory and gas laws, and we're actually going to get into the nitty-gritty of the gas laws and actually give you some mnemonics and some ways to remember these gas laws and how to work them. So it is going to be a lot of math. Make sure you have a calculator out and ready to roll. So let's look at this. The first part is going to be a lot of visual. If I have original temperature, original pressure, and original volume, if I increase the temperature, how do I keep the volume the same? If I increase the temperature, how would I keep the volume the same? Come on. I actually have to increase the pressure. So if I'm going to keep the volume the same, I'm going to have to increase the pressure. If I don't worry about that and I want to keep the pressure the same, then I'm going to have to increase the volume. Because as I increase the temperature, particles move faster and they hit the sides of the wall more often. That increases the pressure. So if I want to decrease the pressure, then I'm going to have to make the volume bigger so there's more room so they don't have to hit the walls as much. Okay, so we can also talk about the number or amount of stuff that we're putting into a container. So if I have 1 mole of something and I want to hold it at a constant pressure, it's going to occupy some volume. If I put twice that many moles, N is equal to moles, by the way, if I put twice that many moles in and I want to maintain the same pressure, what's going to happen to the volume? By how much? 2. Good. So I'm going to increase by the volume of 2. If I do it 3 times, I'm going to increase by the volume of 3 if I want to keep the pressure the same. Okay, so there are relationships here that help us to get the exact laws going on here. So if I change the size of the container, what's happening is in a smaller container we have less room to move. So if I took this class and I took into a class the size that was half of this, we would have less room to move around, right? And we'd bump into each other probably more often. Okay? Because we bumped into each other more often, or the sides of the container, the pressure in there would increase. Okay? Because the pressure increased, we would have, hopefully we wouldn't blow. Volume decreases, pressure increases. So this is something that as they were doing, scientists were doing experiments, they found this to be true. And as volume increased, pressure decreased. So this is something that we are going to be using. It's called STP. STP is standard temperature and pressure. For a gas, we are going to be using always, always, always Kelvin. So 0 degrees is standard temperature, but we're going to use it as 273.15 Kelvin. And anytime it says STP, we're going to know that that is true. It's standard temperature of 273.15 Kelvin. It's also 1 atmosphere. But we need to know from last time that 1 atmosphere is also equal to 101.3 kilopascals, 760 torr, 760 millimeters, or 14.7 psi, or 1.013 bar. We need to remember all of that. So if we need one of those other units at any time, we can use it. Okay? But we're always going to use Kelvin when we're using temperature. So let's look at temperature scales. These two equations down at the bottom, we are going to need to go back and forth between Celsius and Kelvin and Fahrenheit. You'll notice that we know that water freezes at 32 degrees. We know that water boils at 212 degrees Fahrenheit. Celsius is very simple, 0 and 100. The scales of Celsius and Kelvin are the same. It's just the numbers are shifted so that in Kelvin we have no negative numbers, and we've never reached 0 degrees Kelvin, so we are never going to have a 0. Okay? That's important because in the gas laws, temperature is on the bottom. In other words, we're dividing by temperature. So if we were dividing by a negative number, we would end up with a negative volume. That's sort of impossible. Okay, we would end up with a negative pressure. Well, that's not impossible. That's probably, unless I'm making a vacuum, highly improbable. If I divide by 0, I know in math that's undefined. So a Celsius scale causes us problems when we're working with gas laws. That's why we have to use Kelvin. Okay, so Kelvin's going to be something we're going to be converting all our degrees Celsius, all our math, or all our data that we have into. And I am reiterating this. You got to use Kelvin when you're in the gas laws. And again, you got to use Kelvin when you're in the gas laws. Okay, so just remember that. That's a really important thing. So let's do some conversions real quick. 78 Kelvin to degrees Celsius. Do it real fast. Let's see if you get the right answer. What am I going to need to do? Going from Kelvin to Celsius, what am I going to need to do? I'm going to need to subtract 273.15. So if I subtract it, then I'm going to get a negative number. And that would have been a negative number I would put in my gas laws. So I needed a positive number. That's why I do Kelvin. So on B, we're going forward. We're going from Celsius to Kelvin. So we're going to what we call the absolute temperature scale. That's the Kelvin scale, because there is no negatives and no zeros. So on this one, instead of subtracting, you would actually add the 273.15, and you would get 329.15. Okay, do we have any problems with being able to do this, going back and forth between Celsius and Kelvin? This is probably going to be the most common thing we're doing with the gas laws. Oftentimes though, well not oftentimes, occasionally they'll throw in a Fahrenheit, and you'll need to convert Fahrenheit to Celsius and then to Kelvin in a problem. Okay, going forward. So we're going to start with our gas laws. Now, I'm going to give you easy ways, hopefully, to remember them. This first law is the ideal gas law, and the ideal gas law has to be in specific units. But the way that I'm going to tell you to remember it is a little weird. Don't be offended. It's just a way to remember it. Okay? So, ideally, you're not a pervert. What? Okay? Well, I hope you're not. Okay. The way we remember the ideal gas law is PV equals nRT, perv nert. Okay? So it's a way to remember it. So ideal gas law is PV equals nRT. So let's take and break that down. PV equals nRT. P has to be in atmospheres in the ideal gas law. So when I just have PV equals nRT, it has to be in atmospheres. So I need to use the conversion factors to get whatever I'm given into atmospheres. Volume has to be in liters. Okay, it can't be in anything else, it has to be in liters. N is the number of moles. R is a constant that you have to memorize or put on your card. And if you do that, it will tell you what units need to be used in the ideal gas law. 0.0821 atmospheres times liters divided by moles Kelvin. And then, of course, T is temperature, and it needs to be in Kelvin. So we need to make sure that we convert all temperatures when we're using gas laws to Kelvin. Sorry, I need a nap. Okay, we ready to go forward? Okay, so the next law, well, is taking the ideal gas law and solving for R. R is a constant, and so if I have different sets of materials to do, say I had an original pressure, volume, and temperature, and then I get a new pressure, volume, temperature, I want to compare the two, and maybe I'm missing one of these, I can set these two equal because they're equal to R, and R is a constant. So we get a combined gas law, because I'm combining two things, of P1 V1 divided by T1 N1 equals P2 V2 divided by N2 T2. Now, the N's are moles, and moles are hard to change in lab. And so oftentimes we just drop the moles because we're going to keep them constant. So anything that's constant drops out. So we change this a little bit and make it this. So for the most part, we're going to drop out N. So in my notes, if this were my notes, I would probably put the N1 here, but I would circle it knowing that it's most often not there. Okay, it's most often not there. But in a case that it might be, I can put it back in. It always goes on the bottom. So then we're going to go to the next law, and these all are related. These first several laws are all related. So if I know the ideal gas law, I can figure out the combined gas law, and I can figure out the next three gas laws from that. So the next gas law is called Boyle's law, and I'm actually giving it to you in reverse order because they found these laws first and then did these other two, but you can find these by knowing the first one, so that's how I would do it. So I look at the word Boyle's, and I gave you a hint. Boyle's has to do with what? Pressure, temperature, volume. Temperature boils, right? If something boils, we're working with temperature. So we're going to hold temperature constant in Boyle's law. So the temperature will drop out of that combined gas law equation. So we get P1 V1 equals P2 V2. This is Boyle's law. Again, N could be there on the bottom, but it usually isn't. We usually drop it out. Okay? I'm forcing myself to walk away so I don't go too fast. Okay, so then the next one is Charles' law, and these are ways to remember it. And I put a little crown up there because Prince Charles, you know, Prince Charles. So pressure, volume, temperature, which one would be affected? Pressure. He's under constant pressure, being royal, right? So if pressure is constant, then I drop pressure out. And we get V1 divided by T1 equals V2 divided by T2. Again, N could possibly be there, but usually it's not. Okay, then we get to the next law. Don't make fun of the poor people's names. They're two guys. I know. But I say their name a little bit different. I say Gay-Lussac's. That's helped me remember what one's being held constant, because remember we have temperature, pressure, or volume. So I think of sucking through a straw, because I'm going to get volume of chocolate milk I like. So I think suck, so that's volume. So volume's held constant. So we would drop volume out. So we get P1 divided by T1 equals P2 divided by T2. Again, N1 and N2 could be there, usually not. Okay, the next two laws that we're going to hit don't have to do with the ideal gas law, so we have to have a different way to remember them. The next law that we're going to hit is Graham's law, and I think of Grandma. My grandma used to wear some really heavy perfume, And she could come and visit our house and leave, and we would know coming 2 hours later that Grandma had been there because her smell was still there. Okay, so I think of a grandma's perfume because it has to do with how do gases diffuse through the room. Okay, so rate A could be a velocity A, rate B could be a velocity B, and then it's equal to the square root of the mass of B divided by the mass of A. And we call it molecular mass because we add it up from the chart. And it's just to compare how fast things move. So if I had you all line up in a line, and on one side had one kind of perfume, and on the other side had a different kind of perfume, and I had you open them at the same time, and then had you raise your hand the minute you smelled it, we could see how fast one perfume moved compared to the other perfume. Or I could have ammonia on one side versus the perfume and see how fast it moved. We could do it that way. We're going to do this lab that I'm pushing off till next time is a lab that has to do with Graham's law. We're actually going to take, this is going to be a straw, and we're going to have Q-tips in the end instead of cotton plugs. And we're going to put ammonium hydroxide on this side. And ammonium hydroxide, when it goes into air, actually becomes NH3. Okay? And on the other side, we're going to put HCl. We're going to mark how far in that we have the Q-tips. And then we're going to look for this little white ring that will form. And when that white ring forms, you want to grab it the first time it forms and make a mark right on it. Because after time, you can see this one down here, there's a white ring here, and it's actually made a cylinder. It actually spreads apart because the gases keep moving. And when they react, they actually make ammonium chloride, and that's that white ring that we'll see. And then we're going to measure the distance between here and where it started, and the distance between here and where it started. And we're going to be able to figure out the velocities, which one was faster, which one was lighter. Okay, so that's what we're going to do with Graham's law next time. I know this is hitting a dead horse on the head, and we've talked about effusion and diffusion, but I'm going to talk about it again because you do need to know it. Diffusion is like I'm opening Grandma's perfume and it's coming out of the hole, and now it's in the room and it's diffusing through the room. Effusion would be through a small hole, and how easy it is for it to get through a small hole. So a large molecule will effuse through a small hole very, very slowly because it's hard for it to get at just the right angle to make it through the hole. But a small molecule will effuse through a small hole very quickly because it's a small molecule and it doesn't have to hit the hole just right. Okay, so effuses through a small hole. Diffuse, it doesn't have any restrictions. It goes throughout the room. Does that make sense? Okay, so if you look at this box here, this pinhole right here, this would be your effuse. Once it's over here in this room and it starts bouncing around, straight line motion, that would be diffuse. Okay? All right, going forward. Man, I wish I was alive when this guy got credit for this law. This is one of those laws that I call the duh law. Really? You got credit for that? I wish I would have been alive. Basically, he said, if I have a container of hydrogen gas and oxygen gas and chlorine gas, and I know the pressures of each of those, and I put them together in a same container size, all of them in the same one, then all the individual pressures is equal to the total pressure in the original, or in what I put it in. So the total pressure is equal to all the little parts added up. Smart, duh, right? Okay, so this is Dalton's duh law. We use it in lab, and we're going to use it next time like this. We know the pressure out in the atmosphere. But when we go to make gases, we usually have to collect them through water. And as we bubble gases through water, some of that water turns into gas and becomes part of the pressure inside. And so we have to subtract the water of the pressure of the water from the total pressure to get the pressure of the gas. You will need to know both this version and this version. Okay? But it's basically duh. The total is equal to the parts, right? Add it up. Okay, and you need to have a pressure table at a certain temperature to be able to figure out how much goes in. And you'll get that with your lab for next time. Okay, so These are on your paper. And ignore the little noise behind. We're going to use that PTV in order to, when we start working with lots of numbers, it's sort of really hard to see, did I get a right answer? Or is it just calculator throw up? Okay, a lot of kids give me a lot of calculator throw up. They have no idea if they've got the right answer or they don't have the right answer. This is a way to see, oh, I've got the right answer. So if, put your finger on pressure. P. That represents pressure. Whose law holds pressure constant? Charles, Prince Charles. Think Prince Charles. Okay, if I have, so in Prince Charles's law, it was V1 divided by T1 equals V2 divided by T2. So what happens, I'm going to have two of either temperature or volume and one of the other. I'm solving for what I don't have, right? So I'm looking and saying, oh, my temperature went from low to high. So it moved up. If it moved up and I'm holding this constant, then volume has to go up because I'm like tilting the paper. Okay? So when I do my calculations, if my volume wasn't higher than it was originally, I know I did it wrong. Does that make sense? Okay, so put your finger on T, this law. Boils. It holds temperature constant. That was a P1, V1 equals to P2, V2, right? So what if this time I've got two volumes and only one pressure? So I'm solving for pressure. And I know my volume goes up. What's going to happen to my pressure? My new pressure? It's going to go down. Because I'm holding this constant. It's like a pivot point. So if this goes up, this is coming down, right? Okay. All right. So let's go to the next one, V. Hold it on V. Who is V? Gay-Lussac's, okay, or Gay-Lussac's. I call it Gay-Lussac's. Okay, his, if I have two pressures and one temperature, and I notice the pressure's going down, which way is that paper going to pivot if I'm holding temperature still? Down, so my temperature will be lower. Okay, so this is a quick check to make sure that what I've got is the right answer. So it makes a real fast, quick check. So remember you're pivoting, so this would be holding temperature constant. I'm pivoting on whatever I've got, okay? Now, let's do some problems. These are story problems. I'm going to warn you. Take it as you go and pull out what you need. Okay, so I'm going to show you, and then you're going to do it. So, 200 milliliter, what is that? Volume, right? V1, the first volume I came to, 200 milliliters. Sample of oxygen gas is collected at 26 degrees Celsius. What's that? T1, and it's in Celsius. So what do I need to do? Right now, convert it. Do not wait. So the minute I hit a temperature, I'm going to convert it to make sure it's in Kelvin. So I'm going to get 299.15 Kelvin. Everybody okay with that? Okay, going on. And a pressure, oh, P. Pressure 1 equals 690 torr. I don't know if I need to convert that or not, but I always know I have to convert my temperature, so I'm going to wait on that one. Then it says, what volume? Oh, V2, question mark. I don't know what it is. Okay, what volume will the gas occupy at STP? STP, what was that? Standard temperature and pressure. So what was the standard temperature in Kelvin? 273.15 K. Good. What was the standard pressure in torr? I heard it. 760. Good. 760 torr. So it's good to know what that's all equal to. It's not just one atmosphere, because here I got two pressures, so the torr is going to cancel out. I don't have to be in atmospheres. I don't have to convert that. Okay, I've got two volumes, two pressures, two temperatures. What law? What law would have 6 variables? Combined gas law. So P1, V1 divided by T1 equals P2, V2 divided by T2. Okay, I don't have any ends, so they dropped out. Now, at this point, It's basically your choice of how you want to solve it. You can plug in everything where it's at and solve for what you don't have, or you can solve for what you don't have and then plug everything in. Doesn't matter which way you do it. No way's right or wrong. You should get the same answer both ways. Which way would you like to do it? There is no real easier way. It's what's easier for you. Do you want to solve for V2 and then plug everything in, or do you want to plug everything in and then solve for V2? I got one of each. Okay, solve for V2. I'm going to do that one real quick. So if I'm solving for V2 right here, then I'm going to divide both sides by P2, and I'm going to times both sides by T2, right? So V2 then becomes P1, V1, T2, and T1 and V2. No, P2, sorry. See what I did? I put TV on the bottom. T1, P2. Okay, so it doesn't really matter if you plug in the numbers and then just solve each side and then go down, or if you do this first. We did this first, so I'm just going to plug in. So P1, 690 torr. V1, 200 milliliters. I'm writing little because I'm running out of space. T2, 273.15 K divided by T1, 299.15 K times by P2, 760 torr. Now, at this point, I should be able to cross out kelvins, torrs, and be left with milliliters, which tells me I've got a volume. I also need to remember when I hit the divide sign, I need to put parentheses around all of that before I hit equal. Okay, so what do we get for V2? Units will be milliliters, and let's take it as being 200 points, so we get 3 sig figs. Somebody brave? 3. 166. Do I have a second on that? Second it. Any thirds? Yeah. Yeah. All right. Okay, so we can get an answer right here. Now, that PTV that I talked about earlier does not work for the combined gas law. Darn it. Okay, it only works for Gay-Lussac's, Boyle's, and Charles. So, let's go to another problem. What volume, so question mark, volume 1, in liters, so we need it in liters, of air measured at 1 atmosphere. What was that? Pressure. Okay, P1 would have to put in a bicycle tire with a volume. Oh, there's another volume. That's a V2, 1.00 liters. If the pressure in the bike was said to be, pressure to 65.0 psi. Assume the temperature remains constant. So that tells me right away what law? Boyle's. So I'm going to have P1 V1 equals P2 V2, and I can use the PTV, right? So I'm going to look. Boyle's law says temperature's held constant, so that's where I put my fingers, right on the T. And I'm going to go this way because that's where my unknown is. Going from this pressure number 2 to pressure number 1, is it going up or down? Ooh, I don't know. Why? What's the problem here? I forgot a T right here. Sorry, ATM. What's the problem? I'm in different units. I got to be in the same unit. I can't compare things that are in different units. That's like comparing apples and oranges. I can't do it. But I can convert one of them. Does it matter which one I convert? It doesn't. So do you want to go to atmospheres or you don't want to go to PSI? I want to go to PSI. Okay. So I'm going to take this one right here, And in 1.00 atmospheres, how many psi are there? Do you remember? If not, look back in your notes. Something I had you write in. 14.7 is correct. So P1 is actually 14.7 psi. Okay, so now we can say, I've got this. I'm comparing it to this. Did it go up or down? Go the arrow way. It went down. So my pressure here is going down, so my volume must be going up. All right, let's see. Do you want to solve it the way we did last time, or you want to do it the other way? Do the other way this time. Okay, so P1 is 14.7 psi times by V1, we don't know, equals P2, 65.0 psi, times by 1.00 liters. So I'm going to divide both sides by 14.7 psi. That will cancel it from over here, right? And 65 times 1 was just 65. So V1 is equal to 65 divided by 14.7. The psi's will go away, and we'll be left with liters. Give me 3 significant figures. It should be about 4 point something. 3. 4.42 liters. Okay, did it go up? Yeah, from 1 to 4.2, it went up, so I did okay. Do you see how that checks you real quick? Okay, so let's do the next one. Your turn. I want you to try it without me. I want you to try it without me. Okay, how do we do? What did we get for an answer? Can we get an answer? Yeah, what is it? 81.3? So the volume did go up, right, which is good. And I did the little check over there on the side just before I even started, so I knew where I was headed. How many got 81.3? Get it? Awesome. Okay, next problem. Same kind of thing. I want you to try it on your own again first. Then I'll start writing on the board. Okay, so I always convert temperature, even though I might not need it at the end because it might say STP. But here it only gave me one temperature. Because it only gave me one temperature and didn't say it was changing, this temperature is not needed. So that's why I crossed it out. Yes?
The V0, V1.
Oh, V1 twice. I did. That's V2. Thank you. Okay, so we're doing the same thing again. We're still with Boyle's law, so temperature's held constant. I'm holding my finger here. As I'm looking and going this way, volume's doing what? Going down. So because volume's going down, pressure's got to go up, right? So I'm looking at P1 V1 equals P2 V2. This time I'm solving for P2. So V1 divided by V2, plugging in 1.00 atmospheres times 3.00 liters divided by 0.50 liters. Liters cancel, and we end up with 6.00 liters. Did I do that right? Something's not right. Because it's atmospheres. That's right. Thank you. I was so used to doing all those volumes. Okay, so atmospheres, thank you for that catch. And I was going to say, my thing didn't work, but it does work because pressure did get bigger. Okay, so that's where we're going to stop for notes today. So what I'd like you to do, I passed out some little containers, actually some syringes, right? I'm going to bring you a syringe. I'm actually going to bring you a marshmallow here in a minute. What I'd like you to do is take the syringe apart. When you get your marshmallow, this is what you're going to do. You're going to put your marshmallow in your syringe. Then you're going to put your syringe to the 30 mark. Then you're going to put back on your lid. That's what you're going to do. Okay? Then I want you to play with it and see what happens to the marshmallow. Okay?